विवेक शुरू करें.
So we have Dr. Devgar from IIT T02 and he is going to take the second tutorial of our workshop. So let us welcome him.
Well, the topic that I have decided, not I have decided, I have been requested by my friend Vivek that he will be talking majorly in the tutorials for the theoretical aspects of convexities and all. And then he said, can you please speak on optimization algorithms, like the numerical procedure to figure out a particular minimum. Although we have been having idea of optimization algorithms, I'll try to mention a few things which are commonly missed. By commonly missed, I simply mean we know the process, we know how to code them up, but sometimes we miss the typical conditions satisfying which the general convergence analysis happens to be true. I will start with general optimization algorithm. By that I mean descent algorithms. So that the sequence xk that is produced that follows fxk plus 1 is less than fxk. And by that we mean it is a descent algorithm. And then under which general assumption such algorithm will have global convergence. And although there are several different kinds of assumptions, I will focus only on very special three particular ways. The first one is I will get to the details of them, but just to let you know, as if the agenda of this talk or my later talks, it will be majorly on three different convergence analysis depending on the special choices of the step length. As we all know, optimization algorithm, when we consider to develop, there is a general pattern, and then that general pattern is as follows: that we start from an initial point, quite obvious to start, and obviously we have to start a process, otherwise how to figure out the minimum. We start and then we move along a descent direction, d naught, and then along the direction we take a step length of amount, let's suppose some amount alpha naught we are denoting, and then we are reaching at the next iterative point x1, and at x1 we choose a descent direction d1, and along the direction again we are processing with the line search, and then we are figuring out a particular step length, let's suppose alpha 1, and we are reaching at the next iterative point x2 and so on. In general, then this iterative process simply follows the following simple iterative equation, that xk plus 1 is equal to xk plus alpha k dk. And you know, this simple iterative process is being followed to solve a very general problem. The general problem here we are considering very simple statement, that find a minimizer of a function fx, x belonging to Rn, and here in my discussion I will not consider like non-smooth functions, I will just consider only the smooth ones, so that our discussion will go in a simple way, and because I have a short amount of time I will not be able to touch upon the non-smooth algorithms. Anyway, so I am again also assuming here that f is continuously differentiable. Fine. And you know, my research journey was not started with this simple problem. I had a tragic life in my PhD, and my topic was not on optimization. And later on, when I got the PhD degree, then the only one fact that fascinated me to take up this topic, optimization, completely a fresh new topic that was not a topic of my PhD thesis, is just the simple statement of this problem, that depending on the problem statement is just simply this one. Whole optimization is around only solving this problem. All the theories, all the discussion, all the algorithms, computation, everyone, they are striving only to solve this simple problem, that so simple to observe that this is just minimization. The statement is statement here itself, it just ends here. No other, any other assumption and nothing, just this statement, fine. And then we are striving for figuring out several algorithms. And again, all the general optimization algorithms, or rather I must say descent algorithms, because here we are processing through a descent way. There are algorithms which do not follow this decency. I will mention what do we mean by decency and all. Well, so all the algorithms commonly, the descent algorithms, they follow only this simple iterative equation, fine. And depending on different ways of choosing this alpha k, which we commonly call as step length, as if along the direction dk we are moving and then we are taking the step amount of length, and then it is called step length, and here is a descent direction. So this alpha k is commonly referred as the step length and dk here a descent direction. And once I am taking descent direction, then obviously I will be choosing alpha k in a way such that the decency happens to be true if I move from xk to xk plus 1. By that, once I am taking this descent direction to make use of this descent direction dk, I must be choosing this alpha k in such a manner such that in the next iterative point the function value is smaller than fxk. Fine. And an algorithm, an optimization algorithm will be called as a descent algorithm if the sequence xk generated by the algorithm follows this inequality for all xk as long as you have gradient of fxk is not equal to 0. Here to figure out a minimizer of this function f, we are following this process in an iterative manner unless and until obviously unless and until we reach at a minimizer. But you know, this is a really difficult task to assure that we are really leading. Although the function values are moving in a decent manner, but this is very difficult to assure you a priori without a special care. If we just move on following this process, we feel like the function values are degrading, then maybe we will be arriving at a minimizer. Common perception, but this might not always happen. And obviously there is a lot of research on the direction of that this descent algorithm may then end up with one of the points that may not be minimizers. So but we are striving for achieving at least gradient of fx is equal to 0. But gradient of fx is equal to 0 will not assure it is a minimizer. A second order condition we need to check, and second order condition is not at our hand because we are simply proceeding with this equation. Without a special care, there is no way out to say that okay, I am not going to reach at a local maximum, neither I am going to reach at a saddle point. There is a lot amount of research. Obviously local maximum can be easily taken care of, but saddle point is not easy to take care of. By saddle point not too easy to take care of, by that I mean today, although it is a proven fact in 2026 in a conference paper, it is a proven fact from the viewpoint of a dynamical system that descent algorithm, the title of the paper is very fascinating, that descent algorithms always converges to a local minimum. That is the title of the paper. Although they have assumptions and those assumptions to just take care how much amount of computational cost or time we require, they have proved that in an amount, if the function f is a function of n many variables, then today we have algorithm to avoid saddle point, to avoid reaching saddle point in an amount of computational cost, a polynomial of log n. The same authors, they proved in the year of 2012 that it can be, saddle points can be avoided by an amount of computational cost that is polynomial of n, but later they must reduce it polynomial of logarithm of n. Fine, and then when this is side result, I will mention later on in a note when I will provide to Vivek, then where these results are available, those I will proceed, but these are very typical. The papers are not long but very typical to follow the proofs. Even when I started looking at the proof, I took quite a bit of time to understand their results and all. But these are proven facts today that saddle points can be avoided if special care are taken during the algorithm, special steps are taken. Well, anyway, so but let us for the time being forget about this deeper discussion. Here then we are aiming for figuring out a minimizer following this process, and we are striving to reach at a point that is just stationary, and then whether the stationary is a minimizer or local maximizer or a saddle point, that can be taken care of later. General algorithm, they aim for finding just a stationary point, because assuring to arriving at a non-minimizer is difficult. Fine, it may be local maximizer, it may be saddle point. So then our aim here is to figure out a local minimizer, but we have a let us have a common consensus that it is okay for us, we will be satisfied if we reach at least gradient of fxk is equal to 0. Fine, and this process, as I mentioned, is called as a general, this is a structure of general descent algorithm. But a descent algorithm will be called globally convergent if the initial point can be arbitrarily chosen from the globe. By the globe here I mean in which the function is going to be minimized. So from an arbitrary starting point, if I am able to generate a sequence xk for which that fxk leads me to give in the limiting sense that limit k tends to infinity, or if not limit but at least a limit point of gradient of fxk, that is going to be the point 0. Fine, the null vector. Fine, then that will be called a globally convergent descent algorithm. Globally, this term has nothing to do with global minimum. This globally convergent, by that we mean the initial point must be can be arbitrarily chosen from anywhere on the globe. Fine, and that's why the nomenclature globally convergent. However, there are algorithms which are very efficient, such as the Newton method. For them you do not have a global convergence analysis, although today by hybridization we have with Newton and steepest, if we mix up then we have a global convergence, but the general ancient Newton method, there does not have a global convergence. Such algorithms which are not globally convergent, but if the initial point is chosen tactfully, then the algorithm might have a convergence, that the sequence generated by the algorithm may follow limit of fxk or limit of norm of fxk is equal to 0. Fine. Such algorithms are called locally convergent, because this initial point, once I mentioned tactfully chosen, commonly they has to be very close, so at least sufficiently close to a local minimizer or a stationary point. Fine, and that's why they are called as locally convergent descent algorithms. There are also in the convergence analysis, mathematical convergence analysis of such algorithms, there is also another terminology that is called quadratic convergent. By quadratic convergent, we do not mean the order of convergence is equal to 2. By that, or sometimes some book they prefer to not to say quadratic convergence, they say quadratic termination. By quadratic termination, here we mean for a quadratic function, if the algorithm is employed on a quadratic strictly convex function, then the algorithm converges not more than in n iterations. That means by n iteration before reaching at xn, here that xn is not the subscript xn here, by xn I mean here the nth term of the sequence xk. If before reaching at xn, if the algorithm converges, by convergence I mean producing the minimizer of the function before n steps, before n many iterations, then the algorithm is said to have quadratic termination property. So these three things we should be focusing on, and we will be checking whether these three important properties are there for common general algorithms like steepest descent, Newton, quasi-Newton. But I will not describe how those are derived. I will just state what are the chosen decay for steepest descent, Newton, quasi-Newton, but what I will focus is on the trust region method. Commonly this trust region method is not deeply discussed in our formal courses. That's why I chose to focus on this truss region method. I will not discuss this steepest descent, you all are aware of, you also know Newton method, quasi-Newton, their derivations are all easily available, but what is not easily available is the global convergence. Sometimes how to make a Newton method globally convergent, or what is the order of convergence of the steepest descent method for a general function, general this function, that is also not available in sometimes in common books. That steepest descent method, we all commonly say it has a order of convergence is equal to 1, but if I ask you, can you provide a book in which you will find that really it is proving that it has a order of convergence equal to 1, you will be really dumbfounded, fine. And so such things which are commonly not there in our courses, in our, at least in India, so those few things I will try to mention so that things will be enriching for you. Anyway, so as I mentioned that the algorithms I will mention, and then we will just make a cross check whether they have, they will have decency property. By decency property I simply mean this property. Decency property is simply fxk plus 1 less than fxk as long as for all k with gradient of fxk not equal to the null vector. Then we have global convergence property. We have local quadratic termination property. These four things we will try to cross check. For a general descent algorithm, particular cases as steepest descent, Newton, quasi-Newton, that and conjugate gradient, that you are all aware of. And the variation of the algorithms, they depend only on the choices of this alpha k and dk. Different ways of choosing dk and different ways of choosing alpha k, they give different algorithms. And this dk, you notice that whole optimization algorithm, once said by Professor Joydeep Datta, whole optimization algorithm is one-sided. By what do we mean by one-sided? One-sided means, you note that all the optimization things, they depend only majorly they depend only on one fascinating fact, the separation result. All optimization, when figuring out the minimizer, you notice that when figuring out the minimizer, I started with the descent direction, but can you give at least one descent direction for a given function that is differentiable? You will quickly say in minus negative gradient, but not only one. You notice that you have a complete half space, that means set of all d's which are satisfying gradient of f xk d, those are satisfying less than 0, all such d's are descent directions. And out of them, so therefore you don't have just only one, you have not only a few multiple, you have one complete half space. And you notice that when choosing this d naught, then you are completely exhausting this d naught. Once at the point x naught, then to figure out a d naught, then one half space is there, is not it? And then another half space is completely then exhausted, the minimizer is not there over here, is not it? So it is a kind of at one iteration, one complete half space is just said no, not there in this side minimizer, fine. And then reaching so at this side it is not there, so one half space is completely exhausted, not there. Then again intersection of this region, and at this point then we figure out again a descent direction, and for that then again another half space, then intersection of another half space, this then, so intersection. So slowly what it is doing, slowly it is trying to cover the minimizer by a polytopic region. At one side it is not there, then next iteration then another line, it is not there on that side, so now intersection of these two sides. And then so slowly what it is trying to, optimization algorithm, although we are following this, but it is making the use of the inequality, one half space, to choose the descent direction. You have multiple descent direction, all D which are satisfying this are descent direction. Now you have your own way, you choose in a tactful way to make the algorithm efficient, you choose on your own way and you are getting different algorithms, fine. So different ways of choosing dk and also different ways of choosing alpha k, they give different algorithms. For steepest descent you all know dk is minus negative gradient. For Newton, Hessian inverse and all those things you all know. But here I will focus in this lecture on the choice of this alpha k. And here this alpha k, how do we choose this alpha k? Our common sense says that, well, I must choose alpha k such that this decency happens to be true. Fine, at least my function value in the next iteration is not going to increase, and at least degrades, at least a bit of amount of improvement I am getting in the next iterative point, fine. And then choose alpha k, and obviously then we are moving along the direction dk. Whatsoever the number of variable of the function here, whatsoever the n value is, you notice that when choosing this alpha k, we are moving only on a particular direction. My entire focus is on this particular direction, and along a particular direction this function reduces to a function of one variable, is not it? So to choose alpha k, then we are trying to figure out the minimum most value of the function as minimum as possible at the point xk, but along dk, fine. And you notice that this is a function of one variable, only one variable alpha, but here alpha is non-negative. And then if we are aiming to find out alpha k such that this should happen, and you have an assurance that this will happen, at least one alpha k is there because you have chosen dk as a descent direction. So if it is a descent direction, by definition you must have at least one alpha k for which this inequality happens, that fxk plus 1 less than fxk, but you may have multiple one. And then obviously common temptation is that, okay, if I have multiple one, I will choose the best one. By best one, what do I mean? That as much as possible I can minimize, as much as I can degrade the function. So then common choice is you choose alpha k that minimizes this function. So that means it is argument minimum over alpha greater than equal to 0. Common choice, this alpha k. But you are not ought to follow this one. You are not bound to follow this one, but this one will be sufficient to assure this one. Is not it? Fxk plus 1 is less than equal to. And our common sense, okay, I want to degrade as much as possible. So that as much as I can make use of my direction dk, that much let me do, and then I am going to choose this alpha k as precisely the minimizer of the function f, fine. And such alpha k, if we are very strict on, then we notice that to figure out this alpha k, then it is a minimization process, is not it? This is a minimization process to figure out such a minimum. Here again one more minimization. So here then it will be minimization under minimization to figure out alpha k, and therefore if to just figure out alpha k, if we are again employing another optimization algorithm, then computational cost will get higher. What do we want always from the economic viewpoint? As less as effort, but as best as possible. So here then as less as the effort. By effort here is the computational cost, computational time. And then to reduce the computational time, will not be stringent about choosing only the minimizer. If that is fine, that okay, because my aim is to follow this inequation, and then it is not saying that you need to choose alpha k this one. If you choose this one, that is fine, but if you do not choose, then also you have multiple alpha k for which you have f of xk plus 1 is less than fxk, is not it? And if that is so, but if we are very strict about no, I will make use of as much as possible the direction, and then you go for choosing this one, but that there is a red alert that if you follow this one, then there is a hidden minimization inside. At every step, then again you are minimizing a function. On the outer side you have a minimization, but in the inner side, even to choose just this alpha k, at every step you are solving a minimization process, and then again you have to re-employ your algorithm to figure out this alpha k, and that takes quite a bit amount of time. So people figured out this alpha k is very nice, in the sense of with this alpha k we can quickly prove that it has global convergence. You just follow a descent, any descent dk you take up, as long as this follows this one, and this alpha k that we call as the exact step length, and this alpha k will be called, once figured out, it is called as this alpha k is figured by the exact line search process. This is referred as a line search because we are moving along a particular direction, the descent direction. At xk we have chosen dk, and then along dk we are moving. And along dk the entire function reduces just to of one variable function. And one variable function, its minimization is called a line search because you are moving along a particular direction or a particular line, and that's why the nomenclature line search. And then you have, so here is a line search that you need to figure out alpha k, and therefore you may choose the minimum most value of this function or the minimizer of this function, that is okay. But you have different multiple ways of choosing this alpha k. Whatsoever way you do, that will be called as a line search because along a line you are moving. So this optimization is called a line search. And then if you are really stringent that okay, I am very strict to have just minimizer, no other, and then that will be called as exact line search. And here you can easily see, once the function f is differentiable, this is a function of one variable, let us call it as phi alpha. This phi is defined over this one, and if you are stringent about minimizer, you just solve this phi dash alpha equal to 0. That is a candidate of minimizer, fine. And then you notice that here a root finding method you have to employ, and then root finding method means again you will follow numerically some iterative process, computational cost will get really large, fine, because minimization under minimization you have to follow. And this will be called as exact line search. Line search. There are two different kinds. One is exact line search, and another one without much caring about the choice of alpha k. Much caring, by that I mean I am just caring this inequality, not other thing, that I am not making use of this particular dk chosen. You may feel okay, I have chosen this dk with several difficulties, why should not I make use of most of it, and then you may go for minimization, but there is a difficulty, computational cost will be higher. But if we are focusing only on this inequality, then you have other way outs. So here these inexact line search are those search process for which we are not very strict about the minimizer to choose as the alpha k, but we take up that alpha k which is sufficient for this one, and also hiddenly that particular alpha k you choose such that I will have a global convergence analysis, global convergence property I will have. So that is a hidden intention that I need to have at least algorithm for which you have a global convergence property. That is a hidden one that my wish, that is my wish, but at least I should follow this one. And therefore alpha k we are not stringent about choosing by this one, not the exact way, but the other ways, those will be referred as inexact line searches. I guess all of you in the audience, they are all optimizers. Sort of optimization you all have been having a sense of it, and then you know for exact it is simply this one. For inexact ones there are different ways, and in the different ways commonly, at least in India, common optimization courses, they always follow different line search process, like using derivative, without using derivative, then without using derivative means bisection method, then you have the golden search method, you have Fibonacci one. But what is commonly missed in the line search, why this Fibonacci? All of a sudden we start teaching with let us take Fibonacci sequence, and with the help of the Fibonacci sequences, let us go for processing that I have this much amount of length as the initial step length with this much amount of length. By that I simply mean here this function phi alpha. Phi alpha is a function of one variable, univariable function, and here to choose alpha, what we do, not in the inexact, or not in the exact one, in the inexact one, that we take as a sufficiently large step length, let's suppose a range, let's suppose from 0 to some number mu, and then we try to figure out where the this minimizer is there. And for that what we do, like we partition this entire length into two parts, in a very tactful manner, so that the reduced interval will contain the minimizer in that way. Fine. So those are all line searches, but they do not make use of function value. They do not make use of derivative of the function, but they just use the function value. Playing with function values, they keep on reducing these intervals, and those are all line searches like golden search, bisection search, and Fibonacci search. But why all of a sudden Fibonacci number was useful? It is due to the following: that when I am reducing this interval to a smaller one containing the minimizer, in that case the reduction factor after the kth step, it will be this. If we multiply the reduction factors, let's suppose from here I am reducing by, let's suppose, some row length of the original length, or row 1 at the first iteration. In the second iteration again I will reduce a bit. So the reduction factor after the nth step will be row 1, row 2 till let's suppose row at the kth step, multiple times the whole interval length. After the kth step, the interval is reduced to this factor times the original one, and the minimum most value of this one is given by only by the Fibonacci numbers. When under certain conditions, that by conditions I mean I need to have this reduction in such a manner, I divide the length into two parts such that wheresoever I am in, I do not know whether I will be, the reduced one will be this part or that part. I want to make these two parts are equal. Accordingly, you divide in at these 2 points, so that this length and that length will be equal, and so that these are called as uncertain interval. And then reduction of the uncertainty. Uncertainty means I do not know where the minimizer is. Uncertainty is not here due to probabilistic sense or something possibilistic sense. Anyway, but when I am reducing, and to have the minimum most value of this one, to have, because I wanted to have as less, and this factor as less as possible, because I want to contain the minimizer in a small amount of k iterations. So this has to be minimized, subject to this row has to be chosen in such a way this factor and that factor will be equal, and that will give rise that this row 1, row 2, row k, those are nothing but the Fibonacci numbers, f1, f2, f3, f1, fk. Quite fascinating. Common books, they commonly in our the standard books, they do not contain this result, but you will get this result from the book by Chong and Jack. I commonly suggest Chong and Jack's book, An Introduction to Optimization, the one book which I commonly suggest my students to start with, because that is the only one book very rigorously mathematically written, plus very important factor, no mistake is there. I have never found any mistake in that book. And later on also I have figured out that quite a few good universities, they follow only this book in their undergraduate courses. Like MIT also, they follow in their list of textbook, the first one is this book by Chong and Jack, An Introduction to Optimization. Fine. Even in the Princeton University, this book is followed. Anyway, so this result is there in the Chong and Jack's book, but all of a sudden why Fibonacci is used? Golden section is okay, we can sense why golden section is taken, but why Fibonacci is taken due to this factor. Anyway, so you have different ways, exact, inexact. In inexact, we are not much worried about whether this minimization is solved, but we are picking up 1 alpha k, that is sufficient for this one. I will now focus on, I guess I have a few more minutes, like 15. So in inexact, I will consider the common inexact methods. Those are, where is the raster? First I must mention why inexact line searches are important. First of all, there is no guarantee that this minimizer would exist. There is no guarantee. If under our general assumption that the function f is just continuously differentiable, you take off, there is no guarantee that you have such an alpha. For instance, you simply take it to the power minus x, the function e to the power minus x, it does not have a minimizer, is not it? I mean, precisely alpha k you may not have, and so not only that one, but also unless we are really careful about this choice of alpha k, if we just randomly take some alpha k such that this inequality, decency inequality happens to be true, sometimes just the decency inequality will not lead us to have convergence. The sequence generated by x, the algorithm may not be having a limit point. It may be like oscillatory sequence, not having any limit point, or even if it has a limit point, it may not be a minimizer, even if this function is having a minimizer. Much more painful is the fact that after the entire process you are ending up with a point that is neither minimizer, nor maximizer, nor even the saddle point. This might also happen if we arbitrarily choose alpha k just caring about this decency property. I will give you two examples. The first one is the following, that if I take up, so here a kind of, you can underline like drawbacks of the exact line search. The first point is that that e to the power minus x example, and later on for motivation of inexact line searches, follow these two examples, that this alpha k should not be very small. First of all, alpha k should not be very small, that I am taking alpha k, because I know once dk is chosen to be descent direction, then you have one alpha k, but then if I am very much careful, if I am like not optimistic, I am just very pessimistic, okay, let me take one alpha k, I know some amount of length is there in which as the function f is descent, then f of xk plus alpha dk is less than fxk for some alpha in between 0 and alpha bar, because that is the definition of decency of the descent direction dk, is not it? So if I know that I have a small length, then why not to take a very small one, so that will be sufficient for decency property. We may feel so, but if we take very small step length, that will lead us to have not reaching at a minimizer, neither a maximizer nor a saddle point. For an example, you take up this one, simple example, that you take up fx is equal to simply x square, one variable function, and then you start from simply, let's suppose 2, then at the point 2, my initial point is equal to 2, at the point 2 you notice that a descent direction is this negative direction, is not it? I mean, as long as I am at the positive x value, descent directions are on this minus 1, is not it? So here you have then d naught is equal to minus 1, and not only d naught, everywhere as long as in the positive direction you have this minus 1 as a descent direction, and follow this alpha k as 1 over 2 to the power k plus 1 for every k starting from 0, 1, 2 and so on. If I follow this step, then it is quite obvious to realize that then xk plus alpha k dk, then I am reaching on the downside, and then we will see that it is never exceeding 0, and therefore decency happens to be true, no doubt at all. You can quickly calculate, you will figure out that f of xk plus alpha k into dk means here minus 1, as long as this alpha k is positive, or simply let me write dk. This is followed, decency is followed, no doubt. But where does this sequence converge? This sequence converge, let us quickly calculate what is your xk. Xk you can figure out. You notice that the first iterative point is 2, the second one will be how much length we are taking, 1 over 2, right, k equal to 0, so 2. So then minus half. Then after reaching at 3 by 2, we are taking the step of 1 by 2 square, is not it? So 1 by 2 square, and then at the kth step, so this is your x1, this is your x naught, then this part is your x1, then this part till this part is your x2, and then kth step if you are considering, then xk will be 1 over 2 to the power k. and then this is simply your 2 minus half times 1 minus half to the power k divided by half, and then you have simply 1 plus 1 by 2 to the power k. It converges to 1, not a minimizer, not a maximizer, nor a saddle point. Is not it? But it has this property that fxk plus 1, this decency is happening to be true. So then we have an alert here. This simple example is giving us an alert that in order to have that the produced sequence convergent, forget about that okay, it is reaching at a minimizer or not. In order to have that the sequence is going to be produced, then that sequence is convergent, and converging to a minimizer is not, converging to a stationary point is not assured. Forget about minimizer. It is not even a stationary point, is not it? And therefore we need to have a tactful choice of this alpha k. We have to have a care of this alpha k. And here, as this alpha k is taken very small, very small means we are very much pessimistic that very small. You notice that at the third step how much we are taking, 1 by 2 square, then fourth. At the 10th step it is just very tiny step we are taking, and then later on, like at 50th step, it is like negligible, is not it? And therefore we are moving, but this movement is not significant. So we need to have alpha k such that this movement is significant. That is very important. So here a message is alpha k should not be very small. Fine. So here is an alert that alpha k, while choosing alpha k, in order to have convergence, alpha k should not be very small. This we should be keeping in mind. Not only the alpha k should be very small, I will give from the same example, I will produce another sequence that if the function value degradation are not very small, like consecutive steps you take off and then fxk plus 1 minus fxk, if this amount, the reduction amount, if that reduction amount is not substantial, the sequence xk, forget about minimizer, the sequence xk produced may not be even convergent. Such an example is the following. So here from this example we have a takeaway message that alpha k should not be too small. Now next example will give us another message that the degradation of the function value, subsequent degradation, must not be very small. You take the same example, start from same initial point, x not equal to 2, but we take the step length very big. Very big is 2 plus 2 by 3 to the power, or let me just cross check if I am writing correct or not. 2 plus 3 by 2 to the power k plus 1. This much amount of alpha k if we take up, let me just cross check the alpha k that I have taken. It is correct. Yeah, 2 plus 3 by 2 to the power k plus 1, this much. You take this one and then I must also write down the difference. And here you notice that the descent directions alternatively are positive, negative in that manner. When starting from d naught, so here d naught at the point 2 for this function, descent direction is minus 1, but when as my step length is more than 2 length, this much, so 2 and then it will be then crossing this 0, and then here it will be and then again another 2 length, because this much length once I have taken, then it is lesser than 2. Another 2 length if I take up, no, not lesser than 2, it is bigger than 2, right? 2, then it will be 2 minus 2, 3 by 2 half, and then again if I take 3 by 2, then this much step length if I take 3 by 2, this is minus 3 by 2. Then on the right hand, here at this point the descent direction is d1 is equal to 1, d0 was minus 1, d1 is equal to 1, d2 will be minus 1, we shall see it. Here let us calculate what is x2. x2 is, this is your x0, then it is your x1, then x2 is minus 3 by 2 plus 2 plus 3 by 2, then at x2, right, x2, so here x0 it was, then not 1, so it will be 2 square, fine, and this much is your minus, so half plus 3 by 2 square, positive. So here this much length, and then we are getting again minus negative, so fluctuatingly positive negative in that manner we can quickly observe. But the difference if we take off fxk alpha k dk, difference is negative no doubt, but this difference you can quickly see that this difference is less than 0, so decency is followed, but the sequence that we get ultimately is this sequence xk oh my goodness, I have not written down the exact expression of xk, but ultimately what happens, it will, it starts from here, then reaches here, then it slowly settles at only at minus 1 plus 1, fluctuates. This xn, it will be going to be this xk, slowly it will be converging to, it is not converging, fluctuating in between minus 1 and 1, and this sequence is not convergent, and therefore we observe that here earlier alpha k was taken very small, and that's why it is not reaching at a stationary point. Here alpha k is substantially larger, but very aggressive it is, we are taking very big length, and then if it is very aggressive, then also it is a problem that the produced sequence may not even be convergent, and therefore we have two alerts, that alpha k should not be very small, second alpha k should not be very aggressive, very large, and not only that, here is a message that why this is happening. This is happening due to the fact that the difference between the consecutive function values fxk, that is very small, very small. Here this expression I have at my hand, this expression you can observe that it will be very small. This calculation will give you minus 1 by 2 to the power k plus 1, 2 plus this much amount, and this much amount is very small. When k gets, let's suppose 5 or even 10, then they will be very small, right? So this difference of the function value, the degradation, they must be substantial. Here the problem was it was not substantial. Function values are degrading, but in a very slow manner, fine. So these three take away message. First, the step length should not be very small. Second, should not be very big, and the third, that the difference of the function values, consecutive points, that should not be very small. So like everything has to be in a moderate way. Goodness also has to be in a moderate way. Like sometimes in our lifestyle, sometimes it is said you do meditation, but what if we do the entire day meditation? Then whatsoever excessive thing is poisonous. Even a very good excessive thing is also very poisonous. So we have to be very moderate in our life, right? So moderate means here is also an alert. And even in optimization, you should have a moderate style, that alpha k should not be very small, should not be very big. Function value degradation is also should not be very small. Now taking care of all this, the inexact line searches are suggested by three most prominent optimizers. Obviously, Professor Martinez-Ligas is also like a father figure, or like just like infinity to me in optimization. Although sir did not do any work in algorithm, but there are people who really have done substantial work. Those are like this Nocedal, Wright, Nesterov, but these inexact line searches are due to Powell and Goldstein and also Wolf. These three persons, they have derived that how to choose alpha k in a manner such that they produce sequences, they have global convergences. So on the next day, these three topics I shall discuss, that they are geometrical sense, that not just inequality, that this is called your Armijo step length and this is called your wolf, but why they are produced and how they are taking care of these three takeaway messages. Those will be there in those four different ways of inexact line search. That will be the topic of discussion. So next discussion will be on inexact line search. Then another two lectures will be on global convergences with the help of first the exact line search, very trivial one, but we will derive. Then with inexact line search, but not with respect to all the four inexact line searches. We have different line searches today, but the ancient ones, classical ones are these four. Out of them, I will just choose the one that is commonly not there or missed in standard textbook. Today we all know the conjugate gradient method. Commonly when we do algorithm or computation in MATLAB, then Armijo line search, we commonly see that, okay, very easy it is. Inequality, and then you do backtracking and you are going to get one line, one step length, such that you have global convergence. But conjugate gradient method does not work with Armijo line search. Today we have tactful ways of clubbing Armijo line search plus conjugate gradient, but ancient one, the conjugate gradient, it was proven by Joutentzik. He proved that he could not figure out that global convergence of the conjugate gradient, any of the then different variation of the conjugate gradient methods were not really working. So far also there is no proof that Armijo line, inexact line search plus any of the variation of the conjugate gradient fail, dumbfounded. They are not able to prove, or even they are not able to produce that Armijo condition sequence, but they also could not prove. So far there is no proof. Armijo plus conjugate gradient global, but Armijo condition plus wolf, that is, and then Joutentzik quickly derives the global convergences. So four ancient, one after another, they are derived due to the observation that the different methods, they have searches, inexact line searches, and but I will prove the conjugate gradient plus the weak wolf. We have two variations of wolf, weak wolf and strong wolf. Case of the not particular case, by proof with the weak wolf, then with the strong wolf it will be easy. So I will pick and another property is the diminishing step length. Fascinating. Fascinating means one of the most fascinating result I have ever, that people started with the sequence 1 over k, that why don't you take alpha k is equal to us, and then now we have generalization that you take alpha k is equal to positive infinity, but they are square summable. K with this one, but such alpha k may not have descensive property. That has this property. This is called diminishing step size, because this will assure alpha. But with this you don't have this property. F of xk plus 1 is, but still fascinating. Descensive property not there. Convergence of common methods. The most I feel that it was a random choice alpha. People generalized and figured out no descensive property but global convergence. This result also I will try to prove. Fine. So inexact line, next lecture for geometry, from the geometrical perspective, we will go proving of line search, a quick proof with respect to the weak wolf line search, step size, the global convergence proof, and the last lecture I will an algorithm. Okay, thank you all for your kind presence. No, here no. From this example, okay. Obviously, it has dependence on the initial point, but we can also produce a general example. Although I don't think I have not thought on that way. Maybe a dependent, obviously initial point dependent the sequence is produced, but depending on different, maybe if you take a general mu value and accordingly maybe a function can be taken up. So may not be depending only on this particular 2 value. For a given alpha, from where you want to start, accordingly a function may arise for which this oscillating nature of the sequence may happen. I have not seen, I have not thought in that way. Okay. Any more question? Okay.